Next up, I would like to introduce Kedar Tyagarayan, who will be presenting the Aleph Decoding DNS PTR, records with large language models. Kedar is a third-year PhD student in computer science at Northwestern University, advised by Dr. Fabian Bustamante. His research focuses on internet measurement and the use of machine learning to tackle networking problems, with an emphasis on understanding the resiliency, security, and performance of internet infrastructure. Previously, he's worked as a software engineer at VMware and Meta, building and scaling distributed systems and production tooling. It's a pleasure to have him with us today. Welcome, Kedar. The stage is yours.
Thank you. All right. Hello, everyone. I'm going to be talking about the Aleph, which is a project I've been working on at my university with my advisor. And it's a framework for geolocation, specifically using DNS pointer records or reverse DNS records, and understanding them using large language models. So a bit of background. Why is geolocation important? So it has like several different applications you could think of. Troubleshooting, figuring out where the router is that's having latency loss or where a detour is happening. Resilience planning, figuring out where traffic is entering your network and potential choke points and failure dependencies. General topology mapping, like revealing physical paths from city to city, across countries, across subsea cables, and crossing different backbones. Additionally, it can also be used for policy and compliance, meaning you want to verify, for example, if you're in Europe, that your traffic stays within Europe for sensitive data, or, for example, in California, there's the CCPA, and every single different country has different kinds of regulations that you have to keep in line with. Another thing that you might use geolocation for is security, like detecting hijacks, tunneling, and unexpected jurisdictional exposure for sensitive data. And one that I didn't mention here that's also quite important is performance optimization. For example, if you're running a content delivery network, making sure that a client gets routed to the nearest POP to them so that they get good performance. So at a high level, there are two ways that you might go about geolocating an IP address. The first way that you've probably heard of is latency-based, which is basically sending pings or trace routes to an IP address from distributed vantage points all around the world or around a country, and then basically coming up with a polygon based on the intersection of the circles that you obtain based on the RTT measurements. So there's an example there, there's IPmap, right? There's also a lot of companies that do this, like IPinfo. Another way people go about geolocating IP addresses is based on metadata in the internet at large. So that could be, who is, geofeeds. But in this talk, I'm going to be focusing on pointer records, which are basically the host names that operators tag their infrastructure with. And a lot of them encode some kind of hint as to where these devices actually are. This has been a known field for decades now. I think the very first paper written on this was in the 90s, where people basically created manual regular expressions and manually mapped the hint to a particular city or metropolitan area. And recently, people have been trying to apply machine learning techniques. An example of this is Kata's Hoiho. And what we've done is built on this extensive line of research, along with the new technologies that are available, to make this process scalable and adaptable at internet scale. So yeah, some of the ongoing challenges with geolocation are that latency-based methods often fail on infrastructure devices. An edge server will often respond to a ping, but routers along the path or access devices may ignore or drop ICMP-based requests like ping and traceroute that are essential for doing this kind of triangulation. Beyond that, even using pointer records, the hints that you find in them are abundant, but they're messy. Their encoding can change from operator to operator. The same string might mean something different when you're looking at an AT&T record versus when you're looking at an NTT record. And as I mentioned before, the current methods for doing this are brittle and ad hoc. They often use pre-computed geographic dictionaries and manually curated regular expressions in order to map these. And 20 years in, we're still misplacing routers and transit hops in a lot of measurement studies, despite a lot of work being put in for accurate data for end hosts. In the IPv4 space, there's 55,000 plus autonomous systems that may offer pointer records with geohints, but as I said before, it's quite hard to make sense of them. A lot of the hints that you might find in these records are actually meant for humans, and they also lack a standard. Previous talks at NANOG and also previous records have extensively documented the use of airport codes in these pointer records to point to the location of a network device. But as I'll show later, we find that these airport codes only account for about 15% of the hints. And over 77% of them are custom to the operator, varying from silly code to concatenations of city abbreviations and countries. And further, we find that even one location can be referred to in thousands of ways across the entire internet. So here are some custom codes that we've been talking about. So for example, London might be labeled LONGB, and we also see that London can be labeled in different languages, like it might be called Londres, or London with an E, which is in Dutch. Furthermore, we can see that some places are not labeled with the city themselves, but they're labeled by a smaller area within the city. For example, Orange France is using Montsouris, which is a neighborhood in Paris, to label a network device in Paris. Same with the AS20473, which is using Tottenham Hub, which is an area inside London. You can even get more specific than this. There might be street addresses embedded into a pointer record. For example, Comcast uses the hint 350 East Cermak, which is my favorite because I live in Chicago. And 350 East Cermak is a specific street address. It's the merchandise marked, which basically would require someone to look at that, understand where that actually is, and also create some kind of structured mapping to be able to parse this at runtime. Comcast also does this in other places like 111 8th Avenue, which is an address in New York City. As I mentioned before, we can also see people putting these hints within pointer records in multiple languages. As you can see, NTT uses London, which is Dutch. AS3269 uses Londra in Italian. Another AS uses Londres in Spanish. And then, for example, Moscow is labeled in Moskva, and in New York can be labeled in Spanish Nueva York. So there's quite a bit of challenges in creating a way to extract this information and actually use it at runtime. In the bottom left, you can see that across our entire data set, which has over 1.5 billion pointer records, Moscow was labeled in almost 16,000 unique ways. London was labeled in 14,500 unique ways, and New York was labeled in over 7,000 unique ways. So everyone has obviously heard of LLMs, and maybe they can come to the rescue. Because the key insight is that LLMs might be better than us at identifying the patterns within these pointer records, especially at internet scale, where there's 55,000 ASes and 1.5 billion pointer records. So what the system does is it leverages the large language model to classify pointer records into groups. Then based on those groups, we generate regular expressions for each of those classes. Then we map those classes and regexes to actual locations. And we can use RTT measurements and ground truth data from operators to actually validate this data at scale. So now I'm going to be moving on into talking a bit about how Aleph works. So at a high level, there's 3 steps that we take. We divide the process per AS because the assumption is that one AS may use a particular hint differently than another AS uses the same hint. So let's say you have all of the pointer records that belong to a specific autonomous system. The first thing to do is to group them into classes that are semantically similar. So we use a LLM to do that. Now, once you have a grouping, per group you would generate some kind of extraction rule. And what we chose is regular expressions to generate a regular expression that would extract the particular strings within those pointer records that actually refer to a location. And the third step is you need to map that extracted hint to the actual location on Earth, like city, state, country, lat, long. I'll go into a bit of an example of this. So in the first step, for example, this is AT&T. You might have some records like this. They all belong to different second-level domains like PacBell, Southwest Bell, Bell South. And once you send it to the model, you get out a grouping with some smart prompting. You get out a grouping that says PacBell DSL records look like this, Southwest Bell records look like this, and these are some representative examples of those groups. Now, once you have those groups, the second part is to take each group and use the model to generate a regular expression that actually extracts that particular geo hint out of the pointer record. So on the right, those are the two regular expressions that Aleph generates for PacBell DSL and Southwest Bell. Now, once you have these regular expressions, you would apply them to the entire space of DNS pointer records for that AS. And what you basically get back is a group of candidate strings. For example, in the bottom left, you can see like San Francisco 21, Wichita Falls, Texas, Miami. Those are all candidate strings. And again, you use the model to actually disambiguate what these candidate strings might mean. So at the end of this process, what do you have? You have a set of regular expressions, and you also have a key value store that maps what the regular expressions extract to what they actually mean in the real world. So we took this framework and we applied it to 14,616 IPv4 ASes and 4,738 IPv6 ASes. And what we found from this experiment was that 63% of the ASes encode hints within their pointer records. And that means that the DNS pointer space is a much more rich source of information than people would have previously thought. We found 1.3 million unique hint strings that map to 229 countries and 70,380 cities. And we have kind of a categorization of the types of hints that we found. As I mentioned before, custom hints are the most popular, followed by airport codes, and then exact place names, countries, ICAO codes, which is another type of airport code, UN locos, and also a small percentage of them are names of facilities, like internet exchanges. Some interesting hints that we found that we think are difficult for most systems to find are 350 East Cermak, as I mentioned before, also Baires R, mapping to Buenos Aires, Argentina, the Moscow example, and then also the many different ways that one might refer to London. What we've done after that is we've created a website for it, which is right there, the Aleph.ai, which has an interactive search, a REST API, and some documentation for how you might use it. The UI also allows you to try this without any setup. So you can paste a pointer record, you can get what regular expression we used, the extracted hint that we got, and also geolocation inference. The other feature that we've included in this is the ability to paste trace routes. So you might be able to get hop-by-hop geolocation information for all of the pointer records that we can actually disambiguate information from. It's also queryable through a REST interface, so you can use it from any programming language, and it has support for batch queries, and it's designed for traceroute and infrastructure mapping tools. So here's an example of the API itself. you would just send a post request that contains your pointer record and optionally the AS. If you don't include the AS, we will try to infer it using BGP dumps. But if you do include it, then we will just use what you told us. And what you get back in the response is the pointer record, the AS, and also the location info. So for example, this one contains the hint SKT2CA, which we have mapped to Stockton, California. And it also shows you what regular expression we use to extract that hint and the IP address. This is the UI example that you can try. So if, for example, if you just put in an IP address there and you click query pointer, it will give you back the same kind of thing, but in a nicer way to look at it. So that pointer record there says A Montsuri and then blah, 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 Wanadu FR, which is orange. And it will tell you that we infer that the location of this IP address is within Paris. Another thing that we've done is, so the very first version of this only encompassed 2,600 ASes. That covered 90% of the pointer record space. But with IPinfo, we've been working on expanding the system to cover 99.99% of all RDNS records, which is about 20,000 ASes total. And we've integrated this system into IPinfo's production geolocation pipeline, which powers RDNS-derived geolocation for hundreds of millions of IP addresses. And we've also conducted validation experiments of it with 200 million plus IPs for which we have active measurements for. One thing I'd like to mention here is that we are writing a follow-up paper for this, and I'm super excited to be at NANOG because a lot of the operators that Aleph obtains geolocation information for, you guys are here. So we're writing a follow-up paper, so we would love to collaborate and see whether we're right or wrong. So if you guys would like to reach out, my email is on the next slide. This map here basically shows an entire map of every single unique location that we were able to find from the DNS pointer space. So that's 70,000 plus cities across 20,000 ASes in both IPv4 and IPv6. And thank you. That's what I've been looking to talk about.
Do we have any questions?
Chris Rapier, Pittsburgh Supercomputing Center, AS 5050. So how long have you been querying different ASes? How long do you expect to continue to do that to expand the size of the database? And where do you see this going long term? And what sort of value can it provide to some of the other researchers out there that do work in BGP routing, things like that?
Thanks for the question. So part of the work that I didn't mention here is basically we've been trying to evolve the system into a crawling-based system. So the internet changes, but not all of it changes at once. So for example, if you generated these hints and in 2025, a lot of them might be valid still in 2026. But what we're working on is developing a framework for detecting when these regular expressions and hint mappings go stale and regenerating them. And our goal is to provide an open source tool to the research community that gets updated as artifacts become stale. Yeah. Hi.
Hi, Ryan Ryder, affiliation with the United Fiber. When using the LLM to parse the data, do you have it assign any sort of confidence level to its ability to map to a particular location, or is it more of a confidence level on 100% for like country, 80% on the state? It just kind of dives the more local you get, or?
Yeah, so we don't let the LLM give us the confidence. We determine the confidence post hoc. Like for example, let's say you have a pointer record, you get a hint that says San Francisco. Then after the fact, you would validate that with a bunch of measurements to that IP address saying, is this actually a plausible guess or not? So when we did those experiments, we got plausible results for 93% in IPv4 and 88% in IPv6. So using the system, what we would recommend is you grab the hint and then you can mark the ones that are wrong as not confident with your own RTT measurements, basically. Yeah.
Okay, so no remote questions. Any more questions from the audience? I guess not. So thank you, Kedar, for your talk. It was an interesting talk.
Thanks.
Thank you.